Okay, we are going to discuss some homework examples for Chapter 3 of Conceptual Physics. But I'm going to start off with a little cheat sheet. I'm going to present these to you so that you can have them as we do the homework and the quiz. So let's get started with this first section, just position, velocity, and acceleration. These are some formulas for you to use. Now, most of these I've got them specified by X, but they also, if we're talking about vertical movement, they would work in the Y direction also. So first we want to talk about displacement. And the displacement is defined as the final position minus the initial position. And we designate that as delta X. So delta X is equal to X final minus X initial. And the time interval is the final time minus initial time. So we designate that as delta T. So that's equal to T final minus T initial. Now, when we talk about average velocity, that's the displacement just defined above, divided by the time interval defined underneath that. So the average velocity, that's the V with a little bar over it. The little bar indicates average. And so it's delta X over delta T. Well, what is delta X? It's X final minus X initial divided by T final minus T initial. So that's how you find the average velocity. It's the total distance divided by the time interval involved. Now, average acceleration is the change in velocity over the time interval. Well, the change in velocity, delta Vx, is equal to Vx final minus Vx initial. And the delta T is T final minus T initial. So the average acceleration is the X final, V final minus V initial divided by the final time minus the initial time. Okay, I'm going to dismiss this so it doesn't hide the equation numbers. Now we're going to discuss some equations of motion. Now for a constant velocity, Vx, that is, there is no acceleration. Acceleration is equal to 0. The final position, X final, is equal to the initial position plus the velocity in the X direction times T. Now, for you, when you have a constant acceleration, you'll have the final velocity is equal to Vx final equals Vx initial plus the acceleration times time. The average velocity is equal to, and that's the little v with the bar over it, Vx initial plus Vx final divided by 2. I mean, if you have two grades, if you have a 95 and 100 and you want to average them, what do? You add the 95 plus 100 and you divide by 2. So it's the same thing, the V initial plus V final divided by 2. That's the average velocity. And the final position is equal to X final equals X initial plus average velocity times T. Now that looks, number 9 looks just like number 6. The only difference is there's a little bar over the V, which indicates it for average velocity. This one was for constant velocity, so there's no average over it, and that's the only difference. Now, the final position, this one's a little more complicated. The final position is X final is equal to X initial plus the velocity times T plus 1/2 the acceleration times T squared. Now, I don't think I used that in an example, but we did use the next one, the final velocity squared. We have V final squared equals V initial squared plus 2 times the acceleration times the distance traveled. So we're going to use that in one of the equations, the displacement. So v final squared equals v initial squared plus twice the acceleration times the displacement. Okay, now let's go to a new share and get to the homework examples, and those are here. And we're going to use some of these equations. Okay. Usain Bolt's record for the 100-meter dash is 9.58 seconds. What is his average velocity? Well, the average velocity is the total distance divided by the time interval. So that's 100 meters divided by 9.58 seconds. So it comes out to 10.44 meters per second. So that's how you get average velocity. And I don't know that I'm going to pronounce this right. Wade van Niekerk from South Africa holds the world record for the 400-meter dash with a time of 43.03 seconds. What is his average velocity? Same formula. V average is equal to 400 meters divided by 43.03 seconds, and that comes up to 9.3 meters per second. And you can see that's slower than the 10.44, but to maintain that over 4 times the distance is a little difficult. Even Usain Bolt doesn't hold the record for the 400 meters. It's a much more difficult task to maintain that high speed over 400 meters. Okay, number 3. A drag racer accelerates to a speed of 110 meters per second over a distance of 400 meters. What is its average acceleration? And we're going to use this equation 11 that I gave you in the cheat sheet. V final squared equals V initial squared plus 2 times the acceleration times the distance, the displacement. So we solve, basically, well, we want to solve for acceleration. So we want to isolate the acceleration. So we subtract V initial from both sides, and we're left with V final squared minus V initial squared is equal to twice the acceleration times the displacement. Now we divide both sides by twice the displacement. We isolate the AX. The acceleration is equal to the V final squared minus V initial squared divided by twice the displacement, 2 times delta X. And let's plug in the numbers. We have 110 meters per second squared minus 0 meters per second squared divided by 2 times 400 meters. Yes, 2 times 400 meters. Well, we end up 110 meters per second squared is 12,100 meters squared divided by second squared divided by 800 meters. Well, you'll see that this meter takes out the squared term, and we're going to end up with meters per second squared, which is good because that's what we want. It's an acceleration. And the 12,100 divided by 800 is equal to 15.1 meters per second squared. That's the acceleration. That's the average acceleration of the drag racer over that distance. Okay, number 4. What is the velocity of a rock dropped from rest after 2 seconds? Well, the velocity is simply the acceleration times time, but in this case, the acceleration is g, gravitational acceleration, which we round off to 10 meters per second squared. Remember that it's actually 9.8 meters per second squared if you need an accurate number. So it's just 10 meters per second squared times 2 seconds. So after 2 seconds, it's traveling at 10 meters per second. After the first second, it was traveling 10 meters per second. After the second, it was traveling 20 meters per second. What'll it be after 3 seconds? Well, it'll be 30 meters per second, and so on. Okay, how far has it dropped in that same time interval? Well, there we use the V is equal to 1/2 AT squared, but in this case, the A is the gravitational acceleration, G. So I have V here. It should be D. I'm gonna correct that in the handout. So the distance it has traveled, or in this case, the Y is equal to 1/2 GT squared, is equal to 1/2 times 10 meters per second squared times 2 seconds squared. So it's 1/2 times 10 meters per second squared times 4 seconds squared. The second squared cancel, and you end up with 20 meters. Okay. Now, an arrow is shot upward with a velocity of 40 meters per second. How long does it take it to reach 0 meters per second at the top of its trajectory? Well, we're going to use this equation 7. Final velocity is equal to the initial velocity plus the acceleration times time. So in this case, we want the final velocity to be 0 meters per second. So let's insert it and solve for t, for time. Now, I've changed. We've been kind of loose with our gravitational acceleration, but it really is 10 meters per second downward. We want 0 meters per second. We want to know when it reaches 0 meters per second. So our initial velocity is 40 meters per second upward. The gravitational acceleration is minus 10 meters per second downward. That's why I put a minus times the t. That's what we're solving for. So we subtract 40 from both sides, and we end up with minus 40 meters per second equals minus 10 meters per second squared times t. Divide by minus 10 meters per second squared to isolate the t, and you end up with minus 40 meters per second divided by minus 10 meters per second squared. See, the meters per second and the meters per second cancel, so it just leaves you with a single second in the denominator of the denominator, so you can invert that, and you end up with 4 seconds. Okay, let's go on to some other examples. Number 8, a small boat travels north at a rate of 4 meters per second. The river is flowing in an eastern direction at 3 meters per second. What is the magnitude of the boat's effective velocity? Well, let's draw it. Always good, if you're not sure, draw what you're looking at. Here's the 4 meters per second to the north, and here's 3 meters per second to the east. And so here's its effective vector. And how do we find it? Well, we just use Pythagorean theorem, the Pythagorean theorem. The effective velocity is equal to the square root of 4 meters per second squared plus 3 meters per second squared. So if you square 4 meters per second, you get 16 meters squared per second squared plus 9 meters. There should be a squared over here. I'll correct that. 9 meters squared divided by meters squared per second squared. And you end up with 25 meters squared per second squared. When you take the square root of that, you end up with 5 meters per second, and that's your effective velocity. Now, at what angle relative to north is the boat's trajectory? The tangent inverse of 3/4, remember we're looking for this angle, and it's the opposite over the adjacent. So it's 3 meters over 3 meters per second over 4 meters per second. So that's the tangent inverse of 0.75. And you end up with 37 degrees. Now, make sure on your calculator that your mode is set to angles and not radians. So that's one thing to watch out for. But my particular calculator shows tangent -1. Yours may say arctan, or if you're using like something like Excel or something like that, they'll have an arctan. But you should draw it so that you'll know, whether whether the angle is positive or negative. In other words, you should know what quadrant you're in. Okay, I think that's it for this session. So we'll end it here.